In the last video, we talked about Horner's method and how it could be used to find the derivative of a function. In this video, we want to use Horner's method to find higher derivatives of a function. Specifically, in the last video, we wondered about this function, and after having found f of 2 and f prime of 2, we wondered if there would be a way to find f double prime of 2, f triple prime of 2, etc. Now if we think about the way that we found f prime of 2, namely using this polynomial here, we could suspect that to find the next derivative we could just use this polynomial here. Now why am I calling these polynomials? Because what we did in this first step, of course, was we divided by x minus 2, right? This was our polynomial. And this was our quotient. So that would stand for x to the fourth plus 3x squared plus 2x plus 9, right? And we called that q. So we used q to find f prime of 2. Now we want to use this, let's call this q sub 2, and we can retroactively now call this one maybe q sub 1, and even the one before that, the original function, we'll call q sub 0, and we will use q sub 2 to find the second derivative of f evaluated at 2. So let's try to do that. So again, we're given a function in this form, and somehow we need to get these q's into play. So just like in the last video, we will divide by x minus p, we'll call it. We'll divide this polynomial by x minus p. We will get a quotient, q sub 1, and some remainder, r sub 1. And since we actually want q2, at this point we will now sub in for q1. So we will divide that by x minus p and get a new quotient, q sub 2, and some remainder, r sub 2. So we'll just sub that in here, and we end up with x minus p, q sub 2 of x, plus r sub 2, and plus our remainder. And since that's a little bit complicated, we'll multiply that out, and we get x minus p squared, q sub 2 of x, plus x minus p r sub 2, and plus our original remainder, r sub 1. Now we wanted to find the second derivative here, so we'll just add a couple of apostrophes here and say that we're taking the second derivative of all this business. So all we have to do now is do that, take those two derivatives. So we can do that using the product rule here. So 2 times x minus p, and we'll leave that as is, plus, now we'll leave the first part as is, and then the derivative of q sub 2, plus, now the derivative of this is 1 times r sub 2, so we end up with r sub 2. And if we take the derivative of this constant here, that will vanish, of course. So now we're left with this, and we only need to take one more derivative, and we'll be home. So now we have two terms that we want to take the derivative of with the product rule, so let's begin. We get here, the derivative of that is 1, so 2 times 1 times q sub 2 of x, plus, now we'll leave that as is, and we'll take the derivative of that, Okay, now we're on to this term here, plus, we'll take that first derivative, x minus p, we'll leave that as is, and leave that as is, and take the derivative of the second part. So it would be q sub 2 double prime of x. And again, this constant just falls away. And we can already see that we've reached our goal because we want to sub in p for x, right? And if we sub in p for x, then this part is going to fall away, right? And this part is also going to fall away, and this part too. So we are left with, if I take that quite literally, 2 factorial times q sub 2 of p, let's say that what I did here was I said I'm done with that, and here I'm subbing in p. So that's exactly what we were looking for. So it turns out we can find that second derivative evaluated at p. We just have to multiply by 2 factorial, which would give us, in this case, if we do Horner's method, we continue that, so we have 1, we multiply and get a 4, and we multiply again and add, we end up with 46. So if we now multiply 46 times 2 factorial, we end up with 92, and that is the second derivative of f evaluated at 2. Now the question is, what do we do for the third derivative? Well, if we were to go back here and say what we want to do now is to use this, which would be called q3, then we would need to fit q3 into this equation here. So we could do that by substituting in here. So we'd substitute in x minus p times q sub 3 of x plus r3, and we would end up, if we continued that process, with an exponent of a 3 here instead of a 2, and that would mean that we would be multiplying here by 3 factorial. And all of this stuff that fell away before, and a couple of new things, would all be falling away again, because they would always have an x minus p somewhere in them. And so we would end up, in that case, with f triple prime of p being equal to 3 factorial times q sub 2, q sub 3 of p. And as it turns out, that pattern can be generalized to work for any k. So the formula would be the kth derivative of f evaluated at p would be k factorial times q sub k of p. So let's go back and see what that would mean for our example here. So we would continue here, multiply and add and multiply. We'd have 27 at the end of this line. We'd have to multiply that by 3 factorial, which is 6, so 120 plus 42, so that would be 162. And continue here to an 8, so 8 times 4 factorial will be 8 times 24 is 160 plus 32, so 192 for the fourth derivative of f evaluated at 2. And if we continue, we just have 1 times 5 factorial, which would be 120, which is then the fifth derivative of f evaluated at 2. And if we retroactively fit that to what we did in the last video, that would mean that we would be multiplying what we got in the first or the second line here. We would actually be multiplying that times 1 factorial, which of course doesn't change anything, and that gives us the same answer. And our q0 would end up giving us here this 12 that we would be multiplying by 0 factorial, which of course is defined to be 1, which again doesn't change our answer, and we see that the answer that we came up with works in the general case. So we've seen that it works, and now we can see a little bit how it's working. This is our function, and if we take a look at these graphs here, we'll start with the first derivative. This is the one that we looked at in the last video, and we see that f1, or the first derivative rather, has this graph, and q sub 1 multiplied by 1 factorial has this graph. And again, we saw this in the last video, and they cross at the point that we're interested in. If we look at the second derivative and 2 factorial times q sub 2, again they cross exactly at the point we're interested in. Now these curves look different than they did here, but they still cross at the right point. The same goes for the third derivative and the fourth derivative and the fifth derivative, which is interesting since they not only cross at the point that we want, but they are identical. And this has to be the case since the fifth derivative in our case is just a constant. So the only way that these two lines could cross is if they are indeed the same line. And as we talked about the most general case, we could also look at the 0th derivative of f, that being f itself. And these two curves, so also the curve of 0 factorial times q sub 0, are also identical, but only because we defined them to be that way. So that just doesn't just happen to work out, but we defined that actually that way. So that's the trick for higher derivatives. What do you have to do to find those higher derivatives? You have to multiply. Yes, indeed, you have to multiply. Yes, indeed, you have to multiply. Now, why am I saying yes, indeed, you have to multiply so many times and using so many different colors to say yes, indeed, you have to multiply? Well, the reason is, and the reason I'm making this huge exclamation mark, is that I want you to remember to multiply, and I want you to remember what to multiply by. Bye.